Welcome to Machine Learning Foundations, Module 3. This morning we have the pleasure of having Philipp Singer, who's one of our expert data scientists and Kaggle Grandmasters here at H2O AI. He's going to do an introduction into automatic machine learning with driverless AI. So without further ado, Philipp.
Thank you for the introduction. Yeah, as said, I will talk about automated machine learning with driverless AI. But first, let me give you another introduction to myself. So who am I? I'm Philipp Singer. I am a double Kaggle Grandmaster. I'm currently ranked on Kaggle 5th overall rank. My Kaggle handle is C. I live in Vienna, Austria, Central Europe, and I have been with H2O for 6 months now, and I work there as a senior data scientist. I have tackled during my Kaggle journey quite a diverse set of problems in different domains, starting from very structural data sets to image classification, NLP problems. So I have always tried to be really diverse in the types of problems I tackle. So as you can see here, I have won these 3 competitions, 12 gold medals overall, and they are from quite different domains. So the first one is NFL tracking data. The second one is earthquake time series data. The third one is NLP text data, and there are many more also with images and other types of problems. Yeah, and as we said, today I wanna talk about automated machine learning with H2O Driverless AI. And this is where kind of the whole Kaggle story comes together with what H2O AI is doing in their products, is because we try to build, among all the other open source things we have, we try to build tools that help practitioners to conduct machine learning in a similar way as some of the top people in applied data science are doing. So implementing a lot of their tricks, techniques, and make it really easy to apply these things in a streamlined way. And we will go into detail here when we talk about it. So just what you can expect in this session is, first, I want to give you a very quick introduction to the platform. Then we will try to cover a classification case study, as well as a regression case study, and a short outlook to the next sessions. I will try to make this as much hands-on as possible. So I only have a couple of slides, and then we will go directly to the tool and try to learn how to operate with it and see what is possible and how automated machine learning in practice works. Before that, a quick note on the quizzes and hands-on exercises. There will be, as always, exercises and quizzes that will be posted to community learning site within 48 hours of the session. Yeah, please leverage also the discussion forums in order to ask questions. So let us jump into the topic. And let us just try to scope the whole thing that we are talking about. So what are kind of the main challenges in AI today? If you think about, if maybe you are working in some company, maybe you're doing this in your spare time, there are many, many different people and different ways of how to do data science. But what is often an issue, regardless of how and where you do it, is that there is a lack of, or kind of a concentration of talent, and it is hard to get talent. For example, in a company, there's often quite a competition of talent. You need to have not only one data scientist probably in a company, you want to have a whole team of experts of different types of industries, different types of backgrounds in order to really foster your internal machine learning capabilities. And so talent is one of the challenges that many people have at the moment in order to do artificial intelligence. The second thing is time. So how can you improve on how you can leverage the time? So basically, Oftentimes, it takes a long time to do experiments, a long time to go from an initial baseline model to something that you can roll out to production. And the question is, how can we reduce these time efforts to go from initial staging to production? And the third thing, which is also very important, is trust. If you build a machine learning model, how can you trust it? If you want to put it in production somewhere, the people using it need to trust it, or you also need to trust it. You need to understand it. So these three T's, TTT, talent, time, and trust, is something that we rigorously try to focus on in H2O AI, and specifically driverless AI. Just a quick recap, and you have learned already about this. What is AutoML? The term AutoML, automated machine learning, refers to automated methods for model selection and or hyperparameter optimization. And the goal is kind of twofold. First, it is to improve the efficiency of finding optimal solutions to machine learning problems. And it also enables non-experts to train high-quality machine learning models. So there we already have kind of two of these previous T's. We have time, we optimize the time, the efficiency, and talent. We also enable non-experts and maybe more junior data scientists to do really state-of-the-art machine learning models. So we try to solve most of these issues with our tool Driverless AI, and we call it the platform to make your own AI. So why is it called driverless? Because we will also see it in a demo. It gives you kind of this cockpit experience of going from a very initial idea and initial data to a kind of model that is ready to be productionized. So it is really also a driverless experience where you still can manually adjust a lot of things if you want. But in a nutshell, we focus on time and speed, already mentioned. How can we improve building machine learning models in terms of efficiency? We try to build the most accurate models possible. So there, this whole story about all the Kaggle techniques, all the state-of-the-art models, everything that we can try to boost the accuracy is in our tool. And we want to do it end-to-end. So again, starting from data, going to production. So we also focus on deployment. And the final T I mentioned before, trust. We do a lot in terms of explainability. So how does it work? And we will go hands-on into this experience in a couple of minutes. Is you start with some data, you drag and drop the data into the tool, or you load it from some of these many storage capabilities that we have. Automated machine learning is then not only about modeling, but also about exploring, so explorative data analysis. So also we automate some of the functionalities in visualization, in understanding the initial data you have. Then we have the whole functionality for building models, so automatic model optimization. We also allow you to bring your own recipes. This was what I meant before. You can still tailor the process towards your needs. And finally, we have automated scoring pipelines and interpretability. So from data to exploring the data, modeling the data, putting it into production and understanding it. The whole data science pipeline within one tool. And that's what automated machine learning is about. Not only about modeling, of course, this is a very important part, but about optimizing and increasing the efficiency of this whole pipeline of data science activities. How can you use driverless AI? We have this platform Aquarium, which you can find at aquarium.h2o.ai. And there you can just simply click here on the driverless AI test drive, which allows you to run this for 2 hours. So I already tried to maybe, here. This is aquarium.h2o.ai. I started it, and Here you can then just click Start Lab, End Lab, you go to this URL, and you have your own instance of driverless AI that you can play around with, learn how to use it, model a few of the problems. We have a lot of data already on the platform. Yeah, we will go a bit into detail here, but you can use your own instance and try it out. Okay, now that we know what driverless AI is roughly about, how you can use it, let us directly jump into the use cases. And it's always best to learn a tool by seeing it hands-on. And in the past or in the previous session, you have already done a classification and a regression task, and we will do the same in this session, but use driverless AI with different data. So the first one is a classification case study. And just let me quickly recap what classification is about. You most likely know this by now, but just to recap. In classification, we have labels that constitute some classes. They can be binary or multi-class. And the goal is to classify data into these n classes. So for example, if we have mail that is either spam or no spam, we can have a classifier that puts the non-spam into an inbox and the spam into a spam folder, binary classification. Yeah, so we're trying, for example, here, if we have two features and two classes, we try to find the decision boundary based on the features on the classes. And there are a lot of different algorithms that you can use for this task, like linear models, naive Bayes. For example, this whole spam classification is kind of the first larger use case that also naive Bayes has done back in the days already. You can now say back in the days. Then more novel tree algorithms like random forests, and specifically lately gradient boosting, which we will see in action in driverless AI. Of course, also neural networks, stacked ensembles, and many other models. The use case we will try to focus on now is credit card default. So what does default mean? So default means if someone that uses a credit card cannot pay back the loan. So you get a loan in a credit card, you use the credit card, and then you cannot pay it back. So this is a default. And the data we have at hand is customers' credit card payments in Taiwan. And the goal is to predict the defaults. So it is a binary classification task. And the features we have is the amount of given credit to the user, the gender, the education, the marital status, the age of the customer, and the history of past payments. And there is also a link that you can then look into that gives a bit more details about the data. But let us directly jump into the demo. So I have here my own driverless AI system. And basically, this is how it looks like. Okay. I need to restart my session. This will take 2-3 minutes. So maybe let us go for a second back here. Yeah, so the goal here is to, as I said, to classify these cases into default or not. And we will see in a second how the data looks like. I can, in the meantime, go also here. This is where the data is from. You can see here all the different features. We can see that we will have some kind of history of past payments. So they say we track the past monthly payment records. Is actually quite old data, 2005. And we also have amount of bill statements, amount of previous payments, and so on and so forth. There's also a paper published about, you can also find the data set on Kaggle actually, and we will try to use that. In the meantime, let me show you that there is also, if we talk about driverless AI, we also have a very, very sophisticated documentation of the whole tool. And this is something that while you use it and you have some kind of questions, the best thing is really to use this documentation. If you just Google H2O Driverless AI documentation, you get the link and you find it. And here we have all the different techniques and details of the tool within the documentation. So for example, if we want to know about how to upload data sets and so on, we can just type in here data set, and this will be the first thing one does when using. And here we have the whole even a small video of how to add the data and how to operate. And you can just search here and find all of the answers usually that you have. So now that our instance here is restarted, I just need to quickly log in again. So welcome to Driverless AI. This is your driverless experience that you will now encounter. So as I said, what we have here on the top is different tabs for different things. And we will go a bit into detail of some of them. But basically, projects is where you can categorize your data sets and your experiments that you will run into projects. Data sets is usually where you start, is where you have your different data sets in the platform. And experiments is then about running the machine learning models. But let us start here at data sets. I have already uploaded a few data sets here, what we will use throughout these use cases. But what you can do, and also you can do this in your own instance that you can then run on the public platform on Aquarium, is that you just click here on Add Dataset, and you can go to File System. And here we already, if you click on Data, we already have quite a bunch of data sets. And actually, both of the data sets that we will use in this tutorial here, in this hands-on tutorial, are also here in these folders. So for example, you can go on Kaggle, you can find a few Kaggle data sets here. You can go to time series, you will find the second use case we will use here. But the first one we will use is also here located. I have already imported it, and it is these credit card test and credit card train. So this data set is already pre-split into a train data set and a test data set. And this is usually something you want to do yourself beforehand. So you think of how to split a data set into a train and a test data set. And then you do all the modeling on the train data set. And we will go into detail here, like H2O AI does, Driverless AI does then cross-validation on this data set, modeling, and so on. But in order to get a kind of estimate of how well it generalizes, you have a separate test data set that the tool is not touching at all. So it is never really learning anything on that data set. And you can then check how well it performs there. So this is a separate measurement of the accuracy and the generalizability. And this is something you usually do in machine learning modeling, that you first also split out a test data set. So think of this like, if you're used to doing Kaggle, think of this like a private test set that you try to optimize your model for. Yeah, so here in this case, we will start with train, which has 24,000 rows and 25 columns. And the first thing you can do is click on details. And this is now the automated insight that I mentioned before into the data itself. So we see here all the different features in the data set. We have an ID, we have here the sex, so the gender, the education, the marriage, as we mentioned beforehand, and we can directly see how it is distributed. We can see the age, we can see these payment features, and we can see here in the end, the target, which is default payment next month, which is either 0 or 1. 1 means default, 0 means non-default. And we can see it's a bit unbalanced problem, but this is not an issue. So we have more zeros. This will always be the case in these kind of problems. Not the majority is defaulting, otherwise you would do something wrong. But yeah, 5,000 defaults we have in this data. You can also click here on dataset rows to get an overview of the dataset. This is similar to doing like dataframe.head, but you can browse through the different portions. This is very handy to get a quick look of how the data looks like. Yeah, you have the different features, you have the target. So just to get another view. What we can also do here is modify by recipe. I will not do this now, but maybe for the second use case. But for example, you can go here on live code and you can directly do manipulations of the data frame within Driverless AI. Or you can also upload or provide a URL of a recipe. So for instance, we have a large collection. If you Google for driverless AI recipes, we have a large collections of public recipes that you can, so for example, I can click here on data, live code, and then, for example, delete columns recipe. Yeah, you can just copy this code or reference the URL and use this recipe directly to manipulate the data. We will not do this now because the data is fine for our needs. Yeah, so now we have already gained a rough overview of the data. This would be something you would manually do maybe for a couple of hours, build these types of plots, look what kind of features you have, get an overview. So this is already very handy to get a quick grasp of the data. But what we also have is auto visualization. So we can click on visualize here, now that I am able to say it. And we get a few automated plots. So for example, what I find handy is to look at the data heat map. These are all the features, and these are targets. And this is very interesting to see how the data is distributed across the different features. Or what is also very interesting is to look at the correlation graph. So here you have a lever between 0 correlation and 1 correlation. So for example, we can start with limiting it to 0.9 correlation to 1 correlation. And we see which kind of features correlate within this range. And this is apparently these two features. And then we can lower this, and we can see step by step what type of features are correlated heavily with each other. And the lower we go, the more we have here, but we always see kind of red means more correlated than blue. This is very handy to get an overview of what features are correlated. Or we can also go to like skewed histograms, which gives you a view of the features which are quite skewed and gives you histograms. Or we can also click on add graph, and you can manually build a graph. So for example, we could say we want to have a box plot of the age. And now we have a new plot, which is a box plot of the age. Very cool. We can directly visualize different things of the data. Lets us better understand the data. And we can see here that most of the customers are between 30 and 40 years, with the mean somewhere at 35. Let us go back to data sets. So now we have explored the data, visualized the data, we have a better understanding of the data. Maybe we want to tweak something at this point, but now everything looks kind of okay to start modeling. So now comes the big step of modeling. So what we do here is that we click on predict. First time using driverless AI, click yes to get a tour. You can do that. I will not do this now, but you will get a few further explanations of what happens here. So the first thing is that we now are in the process of starting an experiment. So let us give the experiment a name. We are doing it live, so let us call it live 1. We have selected this data set, and the first thing we need to do is specify a target column. So what we want to predict is the default payment next month. So we select this as a target column. We also can specify the separate test data set that we mentioned before here, which is credit card test. Again, driverless AI will not use this data set for any type of modeling, but it will, in the end, apply the final fitted model on this data set and measure the accuracy. We can also drop certain columns we don't want to use for modeling. We can select ID. This will be automatically dropped by driverless AI, but let's select it. Otherwise, we are fine. Use everything. And the next thing usually to set is the scorer. So this is the metric driverless AI will optimize the model for. And for a classification task, we can select a few things here, but you can also go to our recipe section and we have a lot of other metrics that you can use. Usually in classification, as we care also about ordering, an area under the curve is something very reasonable to look for. And then the next thing that pops into our site are these three levers here, these three buttons about accuracy, time, and interpretability. And let me try to quickly explain each one of them. Accuracy is the higher you set accuracy, you can expect the model to be a bit better and to generalize better, to be more robust. So it says also here, higher values should lead to higher confidence in model performance. So this means the model will also run a bit longer, the experiment will run a bit longer, it will do more validation splits. So for example, here we can see that for feature evolution, it is doing 1/4 validation split. And maybe to go through these steps here, so we have here feature evolution and final pipeline. So what Driverless AI is doing, it is trying to find the optimal model and the optimal features. And then it also has a final pipeline, which does again another fold, another cross-validation on what it learned in the feature evolution. Not too important for now, but there are different steps in how our evolutionary algorithm operates within the tool. For now, let us say that higher accuracy means more robustness or more confidence in model performance. I usually start with 5. The larger the problem is, I probably go down here. Time is also about runtime of the experiment. It says how many iterations will the experiment do. And for example, also when is it doing early stopping, how early, and so on. So this is also a time thing. We can also start with maybe 3 or 5 here. 5 sounds fair. And interpretability is also a very interesting setting, which kind of steers the complexity of the features. So we can see here on the left-hand side, feature engineering search space. So driverless AI this is one huge thing about driverless AI, is that it does a lot of feature engineering on itself. So you don't need to do it, and tries a lot of different features that it engineers. And the higher I set interpretability, the less complex these features get, and the easier they might be theoretically to interpret. The lower I set this, the more complex the features can theoretically become. I usually also start with 5. And then we have also what I mentioned before, you can manually adjust a lot of these settings. And this is really a lot that you can do here. We have a lot of expert settings, and I don't have time to go through most of them, but just for you to be aware that there is a lot to set. You can change a lot of things about the experiment, about the models. You can see here the different types of models that driverless AI will run. If you set it to auto, it will automatically decide which ones to try. You can manually select these here. We have a lot of setting about the features, so the feature generation process. We have a lot about time series. We will get to that. We also have functionality for NLP, so state-of-the-art BERT models and similar ones. We have state-of-the-art image models, ImageNet models, ResNet, EfficientNet, and so on. And this whole section about your own recipes, details about the system. So a lot of things to explore. So I really encourage yourself to just browse through these settings. You can always go to the documentation to get more information about what something about here. So for example, if I want to know more about this accuracy knob, I explained very quickly. You can type in accuracy, and here also get some infos about for example, here the experiment settings and similar things. So just browse through this documentation and you will learn more things. For now, this seems fine. So just to recap, we have selected target, we have specified the test data set, we have selected test accuracy, time, and interpretability as 5. We have not changed the expert settings, and we have left Scora as AOC. Now we can click on launch experiment. And now the experiment is starting, and this is where it gets exciting, right? Now the whole driverless experience comes into play. Then the experiment starts. We have just made a few initial settings, and now driverless AI is doing the whole experiment for yourself on its own. And it is already doing things outside of the only modeling, but also in terms of what is important for a proper machine learning experiment, which is building proper validation splits on its own. So it does cross-validation internally. It also checks things like, what are some constant features I need to drop? Is there a data shift? So there, for example, it detects here that there is a possible shift for this feature between training and testing data. So this is interesting. Why is there a shift? So the age is distributed, the sex is distributed slightly different. This is probably not noteworthy, but it still mentions it here. Or if there, it will also detect the leakage. Like if there is a feature that is super predictable of the target, it will give you a warning about it. And you can think, why does this happen? But let us close these, and you can always go here to notifications to see all the notifications. And you can also always go to logs where you see what is happening currently. Here you can see how far the experiment is progressed. So it is already 10% complete. Here you can again see the settings we chose. And now on the left-hand side, it gets interesting. So these are the different iterations of the evolutionary algorithm. And each one is a model fit. So for example, this one is a light GBM model with 18 features, and it gets a score on validation of 0.788. And here in the center, you can see the variable importance. So for the current best model here, the most important feature is pay 0. You can see here the ROC curve and a few other things. So this is, you see during the experiment live how the best model changes over time. So you can see here, we started out with some worse models, and then it jumped up here, and we have some good models with 0.788 AUC. As this will take a couple of minutes, I have already finished this experiment up front, and you can go to experiment to get an overview of all your experiments. So here we just started live 1. We can see it's 15% done, and we can also see here what happens. But here I have an experiment of the same, exactly same settings that I already started and ran before. It ran, sorry, if we go back to experiments, it ran for 4 minutes 30. Yeah, so the whole experiment ran for 4 minutes 30. And it finished with different iterations, different variable importance. But now in the summary, we will look here on the right-hand side. And this is where it gets interesting. So we can see that overall, driverless AI tried 300 different features. And keep in mind, we only had 25 original features. So it did 300 different feature engineerings and ran those and selected only 18 out of those in the end. It ran 16 models trained, and in feature evolution, 14 of 104 models trained. And the final pipeline is 8 models trained. So in this very short time, it did 300 features, and it ran more than 10 different or 20 models. And we can see here the validation score of the final pipeline is 0.77. And then, as I mentioned before, it also calculates it on the test set. And here we get a very, very good AOC of 0.79. So it generalizes very well. So this is something you usually want to check. How close is the test score to the validation score? So this seems like a very good experiment. An AOC of 0.8 is really good for this type of problem. So yeah, we in like 5 minutes, we ran the experiment. And now we can also do other things. We can deploy the model. We have a final model. We can deploy it locally or to the cloud. We can interpret this model. And there is another hour to talk about this, but this will be in a later session, so I will leave this out now. But we have a lot of functionality about explainability and interpretability. We can download the predictions. We have Python scoring pipelines, Java scoring pipelines. You can also download an auto report, which is a very long Word document, basically, with a lot of details about the experiments. You can also click here on scores to get more information into the different models, how they scored, how it's scored across the different 4 folds in this case, all scored very similar, how the final ensemble looks like, and so on and so forth. So this was really just a very quick overview of a first experiment to run, and we will also go into regression in a second. But I hope this gives you an overview. So to recap, we selected the data, we studied how the data looks like, we started an experiment, just gave very rough settings, ran the experiment for 5 minutes, got results with a lot of features that were engineered, a lot of models that were tried, and we have a model ready to be deployed. So thinking back about our 3 T's, time, talent, and trust, we have all of these covered here. Also, trust is here in this interpretation, and as I said, this will be covered later. All right, let me go to the next use case, which is a regression use case with a time series setup. So just to quickly recap again, supervised learning regression labels are continuous, and the goal is to predict the target from data, as is mostly the case in machine learning. We have an X, for example, one feature, and we want to predict Y, and both are continuous. So we might want to learn a function like this. Again, algorithms are very, very vast, linear models, random forests, gradient boosting. So the same models basically that we also heard before work for regression. So actually before we saw LightGBM was best. LightGBM is gradient boosted regression trees or gradient boosted trees. So this falls into gradient boosting. Neural networks, text ensemble, so same thing. So as an example, if you have data about a house, the square feet of the house, the location of the house, the rooms, number of rooms, you have a regressor and you want to predict what the house is worth. This would be a very simple regression use case. But we will try to cover one a bit more fancy, let's put it like that, which is from Walmart, which is also available on Kaggle actually. I have the link down here. And the data is historical sales data of 45 Walmart stores in the US. And the goal is to predict the weekly sales for a given department in a store. So you have stores, you have departments within the stores, and you have the historical sales data for these departments within 45 stores. And for future data, you want to predict the sales, so demand forecasting. The features we have are store, department, date, holiday. So what date it was for each of the sales, what if it was a holiday, and anonymized promotional and markdown data. So whether there were some markdown promotions at that point in time. And without further ado, let us jump back into Driverless AI. So the data set is called here Walmart TTS small train and small test. So again, already split into train and test, and you can find it here if you want to edit yourself. You can find it under data, time series, Walmart. Here, these two. There is also larger data if you want to try that one. So let us look into the data again. If we click on details, we can see the data, the different features. So we know there are different stores. Yeah, actually 45, as we mentioned before, unique. You can directly see it. Everything looks good in the data. We have 14 departments. We have different dates spanning from 2012, May to October 2012. We have weekly sales data. We have the markdown data. We have whether it is a holiday, and there is also a sample weight. We will not use this, so ignore this for now. We can also go into dataset rows and see how the data looks like. Yeah? I also wanted to quickly show you quickly show you how to use a recipe, but just very quickly. So this is basic Python coding. What you can do here is you just have x is the data frame. We can say to NumPy, to pandas, sorry. And then we can just click get preview. So nothing will happen in this case. The data will stay like it is. But we could do something like x, let's say markdown free is always 0, yeah, or something like that. If we click on get preview, you see this changes. If I would click on save, it would make a separate data set. So it doesn't overwrite the current one, it would make a separate. So this is helpful if you want to manually adjust something in the data. But as time is short, let us go into visualizations, which would be the next thing again we check. We have it here for TTS small. We have the visualization. So data heat map, yeah. Again, we can see how the data is concentrated across the features. We can go into correlation graph. I like that one. I really like that one because that is something I manually also check frequently, right? Which features are correlated in what way. Yeah, so very handy. So logically, the markdown features are correlated with date. Yeah, makes total sense, right? At certain dates, there are certain markdowns. Yeah, we can go to skewed histograms, look a bit through. So mostly the markdowns are close to 0. Yeah, right. There is no markdown. Makes sense. Going back to the data set. And as I mentioned, we have a time series setup. So now you will learn 2 more facets of driverless AI, which is time series setup and regression setup. So let us go to predict. Again, let us give it a name, live 2. We need to select the target column, which is weekly sales. And we specify a test data set, which is Walmart test. And we are back to our menu from before. Now we have a regression. It directly detects that. And we need to select a scorer. Root mean squared error sounds fair for this type of problem. And again, now we have a time series setup. So what happens in a time series setup? You want to predict future data from past data. And this is where it gets a bit complicated. First of all, if you manually run such a problem, you need to account for a lot of different things. The first one is to do proper splits of the validation faults, of cross-validation. So I have opened here scikit-learn. If in a second I can click it. Floating. Okay, here. I think most of you have probably already used scikit-learn. Scikit-learn has a very nice overview of different cross-validation strategies. And one of them is actually called, down here, time series split. So let us assume this is our whole data here. And our test data set in this case is in the future. So there is no overlap between time from training to test. So our test data set is somewhere here. And now if we would do a normal cross-validation with random shuffling here, we would partly use data from the future to predict the past. This is not what we want to do. So we want to do some form of time series splits where we always only, so this would be a 4-fold, where we always only use the previous data, the blue range, to predict this fold here. And we do this stepwise. So if you do this manually, you need to really think carefully of how to do this. And we have implemented this fully functioning within driverless AI. So what I can do here is that I click time column and specify the time column, which is date in this case. So date already detects how long is the whole test data set. So what is the forecast horizon? And the forecast horizon is the range of the date for the test data set. This is also, by the way, in our documentation. You can just look for time series and you will find it. And there might be a gap between our training data and the test data. In this case, this is not the case, so ignore this gap here. So let's say the test period has two months period. In our case, Driverless AI directly detects this as 26 weeks. Yeah. So it directly detects that that this is roughly 6 months or something like that, right? And it directly detects this, and it will do the validation folds. And this is a bit tricky to explain very quickly, but it will do the validation folds of the same size as the test data. So it will try to replicate the data you want to apply it on in the future. And this means that in our test data set, we want to do demand forecasting for 2 months in the future. So it makes sense that we split out 2 months portions of our training data subsequently. So these parts here will be 2 months. Then we go back 2 months. Then we go back 2 months, 2 months. And we always only make the folds on historic data before those 2 months. So this is what this forecast horizon looks like. And the next major thing that Driverless AI is doing is that it is automatically building lag features. So if you do a time series experiment yourself, you need to think a lot about how to build features. So how many lags do you go back? Like the sales, you would probably build a feature for this department in this store had sales of this amount in the last 2 months before, 3 months before, 4 months before, and so on and so forth. And this is a very, very tedious process. So Driverless AI is automatically building these type of features. We will see this in a second. And you can also say on which groupings the lag features should be built. As we are interested in department within a store, it makes sense to select these 3 things as groupings. Let's select 555 here again. And in expert settings, we can change a lot of things for time series. Let's leave everything as default for now and launch the experiment. So again, took us a couple of minutes. Of course, I have experience doing that. But if you get a little bit of hands-on experiments, this is really quick to start. And this would be a baseline model you can get out of the box, ready to deploy it very, very quickly. Again, we have possible shifts detected for Markdown specifically, makes sense. Markdowns probably don't extrapolate to the future that well, so we might think about dropping that, but probably they will not be even that important. And the model is starting to run with different features. Here is now in regression case, we can see the residuals, but as this will take a couple of minutes again, let us go back to experiments. And let us go to the one I already finished beforehand. This one took 30 minutes. Yeah, time series is a bit more complex. We have a lot of features to try. Yeah, let us really. So root mean squared error is at 7,007. It loads a little bit. Yeah, wait a second. It needs to load all the iterations. So you can see it improved quite a bit throughout the whole experiment. It ended up with 7,300 on validation. And spoiler alert, on test, it works really, really well with a way lower RMSE. So really good generalizability of 3,500 RMSE. But what is important here is the variable importance. And here you can now see automatically, again, we have only 11 columns, and Driverless AI tried 386 features, out of which it selected 60 in the end. And it did all the important features are automatically generated by Driverless AI, which are lag features like lag of target for groups, department, and store by 26 time periods. So it goes back 26 time periods, takes the record from that time point and uses it as a feature. And so on, different lags. And also it does things like exponential weighted moving average of target lags. So also a bit more complex features. Or what is the day of the year? Automatically derived features from the date. What is the week? Again, lag features, and so on and so forth. So this is very, very helpful for time series experiments because again, this is a very tedious process. Yeah, we actually, for feature evolution, we trained 420 models here. The final pipeline is then just one model. And again, as I mentioned before, the validation score is higher than the test score. This is usually a good sign. It generalizes very well to the test score. Now we can also click on insights here, and now we can really nicely see how the validation folds are built. You can see here that the first fold is exactly these 26 weeks from November 4, 2011 to April 27, 2012. And it only uses this yellow part before to train. Then the next fold is going back and so on and so forth. This is the final pipeline. This is actually the feature evolution. Here it is even here it is also for the final pipeline. We can also go to scores and see the different scores of the folds, yeah, over time. So the folds in time series experiments are usually a bit more diverse because they cover different time periods, but you can get an overview here. Again, we can do all the things I mentioned before, like deploying, interpreting, scoring, downloading predictions, and so on and so forth. Yes, so we are already out of time. So let me just quickly go through what's next. We have hopefully a couple of minutes for questions in a few seconds, but yeah, next time you will learn about how to use our open source tool for automated machine learning. There's also some more information about the quizzes and study groups. So yeah, study group for each module will be held on Saturdays. Ask Me Anything will be on Sundays. And again, don't forget to do the quiz too. Just some info about resources, and that's it from my presentation. I know it was sometimes a bit quick, but I hope to have given you a quick overview of driverless AI. And I mean, that's what it is. It is quick. It should be quick. It should be quick to run experiments, to get insights into data, to learn about the models, and even put them into production in the end. So thank you. Okay, I will try to cover the questions. Is that okay, Parul?
Yes, absolutely.
The first question is, what is workflow or how to validate the result in real-time prediction after model deployed into production? Yeah, I mean, that's a very interesting question. So first of all, we have a separate tool, which is called ModelOps, which is, I have no time to go into detail here, but which is then a lot about how to deploy, how to monitor and deploy the models in production. But generally, the workflow is quite simple. You can track the predictions, right? You know what predictions the model puts out, and you track the actual labels in the end. And you again collect the labels of the new data as it comes in, and you can evaluate it live. So this is really good practice to have some kind of continuous evaluation of the models in production in order to also quickly figure out if some main things change over time, like there is a shift in features, there is a behavior change, and your model suddenly doesn't perform well. The whole thing we do with time series is also to backtest the models, and this can give you already quite indication of how well they can perform in future across different periods. But it is important to continue to track the actual labors and evaluate your models live in productionized environments. What is cross-validation journaling and how is it used generated in H2O? I'm not 100% sure about the question, so maybe you can precise it. But basically, cross-validation, I covered it, I think, quite vastly. In Driverless AI, we have a lot of different techniques that we employ for cross-validation. So like we covered time series, we covered IID, and all of this is done automatically fitting to the problem. But of course, you can also steer it. So you might have some manual adjustments you want to do to some folds. You want to do group folds. You want to do your own folds. So we give the flexibility there. But this is something big that is automatically done. And this is, I think, one of the most important things in a successful experiment, to do the validation properly. Okay, next question, I will read it out. So does H2O attempt hyperparameter optimization for all of the various models? Or is this something we have to do to manually adjust? No, I did not talk too much about it, but this is automated machine learning. So we do all the hyperparameter optimization within the tool automatically. It is not just fitting, let's say, gradient boosted tree with default settings. No, it is automatically optimizing all the parameters next to building all the features. So it is really two main things. Building the different features, doing feature evolution, seeing which kind of features work, and doing the hyperparameter optimization for the models. Those are kind of two main components. And then around that, there is all the important stuff about validation, drift detection, leaks, interpretability, deploying, and so on and so forth. Okay, we got that. If time permits, can Philipp briefly address when different models are better suited for certain types of problems or data sets? For example, trees are better for unbalanced data sets. I think this is a very interesting question. And this is also something that Driverless AI tries to figure out on its own, right? I think in general, for many of these tabular problems, like we now covered, two tabular dataset problems, with one being time series, one being IID, is that gradient boosted trees work nowadays mostly the best. If you tune them, which is AutoML doing, AutoML is tuning them, and you provide the appropriate features, which is also done by AutoML. So it is, from at least my experience, it is very hard to beat gradient boosted trees. And they're not that black boxish. So they also have all the functionalities afterwards for interpretability, explainability, and so on. So I think these are the go-to models for these type of problems. But of course, sometimes it can be good to start with maybe simpler models, like linear models, maybe even random forests. But if you use random forests, you can, in my opinion, directly go for gradient boosted trees. Neural networks are mainly shining if you also tune them a lot. We also have neural networks, feed-forward networks in Driverless AI. But usually neural networks or deep learning specifically shines in NLP and image problems. And we have those as well in Driverless AI. You can fit image models, you can fit NLP models, and we have their state-of-the-art models for Roberta, for example, for NLP, or efficient nets for images.
Okay, then I think we're done with the questions. And thanks a lot, Philipp, for the wonderful session. And for others, if you have any more questions, you can join Siam on the weekend, Saturday and Sunday, to discuss more about this session. So thank you, everybody, and have a great day.
Thank you, everyone.